We can start it. Good afternoon, everybody. Today we're connected here for the fourth session of this ES MRMB course about MR physics and the basics of MR sequences. Most of you will know the speaker of today already, because the first session of this course was taught by him too. Dr. Santini from University of Basel. He is a group leader in MRI research, expert in MRI physics and MRI safety. Deals with quantitative imaging, mostly applied to muscle radiology and to artificial intelligence. Today's lecture is going to be about clinical sequences and quantitative imaging. I will soon let the speaker start his class. I'll kindly ask all of the participants to mute their own end of the conversation so that we don't have background noises. And whenever it's a dedicated time for questions, the speaker will ask questions to the audience. You can either activate your microphone and ask the question orally, or you can type it in the chat and I will read the question for you. Thanks, everybody. Dr. Santini, thanks for being here today, and I'll let you go ahead with your talk. Thank you very much.
Thank you, Dr. Sanvito, and thank you again to ESMRMB for letting me do this. It's always a pleasure. Welcome, everybody, also from my side. I hope that I didn't bore you too much the first time and that you will enjoy this module as well. So I will have maybe a little bit of interaction during the presentation so that we keep it fresh. I could have set up some polls, but yeah, I was probably a little bit lazy and I didn't want to bother the ESMRMB office too much. So we will just do it kind of old school using the chat. And if someone wants to talk, they can also talk. So we are here at module 4 about more clinical sequences and some introduction to quantitative imaging. But actually, I would like to call this module hacking the contrast. Why do we hack the contrast? We know that with MRI, we are really free to do a lot of things. We learned that the basics of MR sequences in the end are very simple. So we have our equilibrium state, then we have some excitation, and then after the excitation, we wait for a little bit. And during this time that we wait, we have some progression, and we also have some relaxation processes. So thanks to this, we know that we can modulate our contrast by doing, for example, a saturation recovery, which is one of the most basic contrast, and then you will get a T1 weighted image. Here you recognize that the blood is black and the tissue is brighter. Or we can do something like a spin echo T2 weighted image, and we obtain these just by modulating the distance between TR and TE and RF pulse and so on. But can we do something better than this, or at least something different? Well, I will try to convince you that we can, and we have to go, however, a little bit beyond what we've talked to so far and what you've seen so far. On the one hand, we can add some bits to our sequences, and we will see what kind of bits we can add. And on the other hand, we can also just use the information that we already have, but we might want to look into some unexpected places to find information where we wouldn't imagine. So already a couple of examples. Here we have an image of, I don't know if you all recognize it. It's a wrist. The radiologist most probably, yes. The common people like us probably know. This is a wrist, but this is a brain. This everybody knows. So you see that here we see a lot of bright structures, and if we want to see the joint here, the wrist, we want to actually see what happens between these bones. So here there are bones, here is muscle and fat. So what we might want to do, we might want to get rid of the fat. And if we do that, we obtain some very nice image like this, where we see all the space between the inside the joint. We can see the cartilage and so on. This is a brain image. Here we don't really have fat. I mean, we would have probably fat somewhere here in the skull, but we don't really care about it. But we see that there are lots of dots here. So there might be some lesion here. What can we do? We can do some magic, and we suppress all the free water in this, and we realize that a lot of these dots were actually vessels or CSF, but some of them were actually pathologies. So if we go back, we see that we cannot really distinguish easily which dots are good and which dots are bad, but by doing some enhancement, we can very clearly highlight the pathology here. These are most probably MS lesions, if I remember correctly. So the first thing that we have seen, these are both examples of suppression. The most common suppression techniques that you have are fat suppression, and these you've already seen in other modules. But you can suppress not only fat, but sometimes you want to suppress fluids, or sometimes you want to suppress also other kind of tissues. So let's examine a little bit more into detail. I will not go very much into detail because these are some of these things, especially in terms of fat suppression, you've already seen. But I want to make a recap and put a bit of all the methods that we have together. So the most important suppression is fat suppression. I could probably use some fat suppression myself, but at least I can do it in the image. So we have a bunch of techniques that we can use for fat suppression. One is fat saturation. Otherwise, we can do water excitation, or we can use inversion recovery methods. And finally, we have the Dixon methods. So how do all these methods work? In principle, we have two sources of signals in MRI. These we've partly seen in the first module. For sure, you've seen it in the basic course. And these sources of signal are the protons in the water, but also the protons in the fat. So these are fatty acid molecules, and is a simplified structure. Here you have carbons, and all around you have protons here, and these are oxygen atoms. If you go and see the characteristics of the protons, we see that they are very different from the ones in the water. First of all, we have some chemical shift that is different from water. So here we have a chemical shift of 4.8. Remember, we talked about the chemical shift in the first module, that it's always referred to silicon oil and blah, blah. So water has a shift of 4.84. And the highest peak in the fat, you see that actually the fat has many peaks because it has many atoms, but the highest peak has a 1.3 ppm. So the difference between the peak in the water and the peak in the fat is 3.5 ppm. This is nice because it's always the same at every field strength. So this means that the two atoms of the hydrogen in the water and the hydrogen in the fat precess at different frequencies after precession. So these are a schematic. The water will precess at a certain frequency, and the fat will have different frequency. But we can also distinguish water and fat by their T1 and T2 values. We see that the T1 value of water is very high. Either it can be adipose tissue or nitrolipid, is anyway in the order of thousands. And the T1 and T2 of fat are much shorter. T1 is around 280. Of course, it depends on the field strengths. So we have these two tools. We have the frequency and we have the T1 that we can use to separate water from fat. So this means that we have a bunch of methods that can be classified into methods that rely on excitation, which are methods that there are methods that aim to not have signal from fat at all, and then only acquire the signal from the water. And then you have methods that acquire both water and fat, but in a way that you can then separate afterwards. As you have seen, there are many peaks in the fat, so it's very difficult to suppress all fat signal. So if you want to really have a completely fat-free image, it is very hard because you would need to identify every single peak in the fat molecules, and this is very rarely done. However, the methods that we have work quite well. The first methods are the excitation-based methods, and the aim is not to obtain any signal from fat. They can be based on chemical shift. The two methods based on the chemical shift, so the different resonant frequency of the water and fat, are called the fat saturation method and the water excitation method. In the fat saturation, we have the water and fat peak, and we first put a pulse that is only selective to the fat. So we are only, let's say, exciting the fat. But after exciting the fat, we destroy the signal. So if we destroy this signal, then we will only have the water peak, and then we can do a normal acquisition. So we prepend this fat saturation pulse that has a frequency which is different from the water frequency. The result that we obtain is something like this, which is generally quite good. You see the intravisceral fat is not badly suppressed, but it is dependent on B0 because, of course, if the frequency of the fat does not match the frequency of the RF pulse, then you have this residual fat signal. Another option is to not excite the fat at all, but use a special pulse that is divided into two pieces, and first excites both the water and the fat at the same time. Then it waits for a little bit until the water and the fat spins diverge, so they precess so that they are into opposite direction. And then the same pulse is applied, and then you see that the fat spin goes back to the longitudinal state, whereas the water spin goes into the transverse state and then generates a signal. This is a very convenient pulse because it has a very low SAR, because you have a big pulse, let's say a 90-degree pulse that is split into two 45-degree pulses. This helps a lot for the SAR, but it's also very slow because you have this waiting time here in the middle. So it has pros and cons, but you can obtain a very nice fat suppression here. After the frequency-based methods, you have the T1-based methods. And this is actually opening now a very broad class of sequences, which are the inversion recovery sequences. Before we actually do the excitation, we will apply an RF pulse that is a 180-degree pulse. And here I have an animation. The 180-degree pulse will not excite this pin, but it will just make it rotate by 180 degrees until the opposite direction. So it will go like this. And then you see, after it's excited, not excited, but inverted, this magnetization will start recovering along the longitudinal axis, so it will not produce any signal. It will start recovery, and at some point it will reach a small state or a zero crossing, and then you can excite, and then you can obtain the signal from the excitation. So this is in general how inversion recovery works. When we plot the longitudinal magnetization in terms of inversion time, we see that the different tissues have different recovery curves. So they start from -1, and then they tend to go back to their equilibrium state. While going back, they will every one of them will cross the zero, but they will cross the zero at a different time. So if we have a short inversion time that matches the time in which the fat crosses zero, then when we excite the system, or we excite the slice, we will not have any signal from the fat, but we will have still signal from tissue or from blood. So this is the concept behind the STIR method. STIR means short tau inversion recovery. It's short tau because we have a short inversion time here. This is the shortest of the inversion recovery sequences, which is aimed to suppress the fat. This is an example of a STIR sequence in the heart. It's used to visualize edema in the heart because it's a T2 weighted sequence and we don't have any signal from the fat. However, you see that the SNR here is quite bad. This is quite bad because when we're inverting the fat, we're actually also inverting the tissue and we're inverting the blood. So when we invert the tissue here, we lose some signal before we actually acquire it. So inverting the fat in this case will also lead to a reduction in a tissue signal. So what is sometimes done? Instead of using a normal inversion pulse, you can use a spectrally selective inversion pulse. So like you were doing for the fat suppression, before it was an excitation pulse, now you do an inversion pulse, but it is also only targeted to the frequency of the fat. And this is the principle between the SPEAR with this spectrally selective inversion recovery, or SPARE, which is spectrally selective adiabatic inversion recovery. Adiabatic means it's just a more accurate 180-degree pulse. So what you actually have is something like this, where you have the signal from the fat that is inverted and then crosses zero, but the tissue does not lose any signal, and then you have a very nice image like this. Unfortunately, the SPARE or the SPEAR cannot be always used because since it is also spectrally selective, we reintroduce the dependency on the B0 in homogeneity. So the advantage of the STIR is that it's very, very consistent, very, very robust with respect to B0 in homogeneity. Finally, we have the Dixon methods. The Dixon methods are a bit of a different class. So we do not want to suppress the signal of the fat at the origin, but we acquire the signal of the fat and we separate it from the water signal afterwards. The easiest implementation is the 2-point Dixon. And what we do is this. Imagine we have the water and the fat together. We excite both of them. And then we acquire one first echo where the water and the fat have the same direction. So it's called the in-phase signal. And it's something like this. You see, everything is bright here because water and fat have more or less the same brightness. And then we wait for a little bit until the water and the fat go out of phase with each other. And this time we acquire again, and this time the signal from the fat will be subtracted from the signal from the water. So you see very clearly here these boundaries, because here you have water and fat and you have this subtraction of the signal. So once you have these two images, you just do a very simple algebra and you obtain a very nice water-only signal and a fat-only signal. This is a very robust technique, very important because you get two images for the price of one. But of course, you need to acquire two echoes, and it's only available when you actually have gradient echo sequences, because you see this out of phase effect. Of course, the 2-point Dixon has some problems because in some cases you might have a situation like this. We have you try to reconstruct the water and fat, but the signals from the water and fat are experiencing a B0 in homogeneity here. So the signal that actually goes out of phase, instead of being the one from fat, is the one from water. And then you don't know anymore if the output has to be water or it has to be fat. And you have these very characteristic swaps. Here, this should be water-only signal. This is in general a fat-only image. So you see the subcutaneous fat here is white. And here there should be very, very little fat, but because of B0 and homogeneity, this appears bright, and this appears darker, even though it's 100% fat. This is because if we have no off resonance, then the water basically has no oscillation, whereas the fat does. But if you have a large off resonance, then you push all the oscillations into the water signal, which is the blue one, and you have no oscillations residual in the fat signal. So you cannot discriminate. What you actually do then is you acquire more echoes. You can, instead of doing a simple algebraic reconstruction, then you need to have models. It's a little bit more complicated, but you can then also estimate the B0, and you can estimate also other parameters like the multiple fat peaks and the relaxation times and so on. These methods are called ideal, and other derivatives here. There's some references to this. Okay, so we've talked a little bit about the various methods. I have talked a little bit about the characteristics of each. I have a question for you. If you have a metal implant, what suppression method would you use? Would you use a fat saturation method or a stir method? Now I will open the chat myself as well. So I encourage everybody to just write 1 or 2. Wow. Okay, very good. Are you sure? Are you very, very sure about your reply? Now I'm muddling the water. Okay, I see that the consensus so far is 2. And in fact, yes, the correct answer is 2. Everybody knows that, but of course, if you have a metal implant, it means you have a strong B0 inhomogeneity. And so the fat saturation, which is based on the spectral characteristics of fat, is not very well suited, whereas the stir is based on T1 and will achieve better performance. Okay, so this was the first block, and we talked about fat suppression. We have what excitation-based methods that aim to not have any signal from the fat, and they can be water excitation or fat saturation. And we have the various inversion methods that also are excitation-based methods, or the acquisition methods, for example, the Dixon. Does anybody of you have any question regarding the fat suppression techniques?
Okay, we have a question from the audience. How do we calculate TI inversion time?
So there are some tables. So for the fat, it is quite well known. Of course, it depends on the field strength, but usually you have tables, and in some cases it's even hard coded in your system. You just activate the stir sequence, and it's calculated for you. It's quite fixed, so you don't have to calculate the inversion time. We will see a bit later how we can calculate the T1 based on the multiple inversions, which is the beginning of quantitative imaging. Okay. Any other question? What method would be more sensitive to evaluate bone marrow edema? They can all be quite sensitive. So these are fat saturation methods. So usually bone marrow edema, you will want actually probably Francesco Sanvito could know better than I do what kind of clinical sequence you would use.
As far as I know, we usually use steers, I think, in the spinal. I'm thinking spinal when you say bone marrow edema. Of course, also other joints can have that, but we don't use Dixons much for that application, as far as I know. But sorry, you don't need to interrupt, so you can go on.
No, it's exactly what what I was hoping for. Yeah, so you definitely use T2 weighted sequence, usually turbo spin echo based. I think that the fat suppression method, it depends on your vendor what they have it better implemented. We sometimes use spare, but it's not super used. Stir is very robust, but also FATSAT can be used, or water excitation. Really, anything. It depends how your sequence is set up and what gives you the best results.
I have one quick question about the inversion time that was brought up before. Would that, so in stir sequences, right, would that depend on B0? Meaning, is it different at 1.5 Tesla compared to 3 Tesla?
Yes, it's different. I don't remember exactly the values, but you have tables.
No, of course.
Just Google it. Okay. I think we should move on. Maybe if there are some other questions, we can just answer in the end. So let's move on, still in the suppression vein. We started with this example. So this was one example of the brain, and we see that by suppressing actually the fluid that is around the brain, we can highlight the sequence, the lesions. This fluid suppression is very important. It's so important that actually has its own name. It's called FLAIR, and FLAIR stands exactly for fluid attenuated inversion recovery. So by now you know what inversion recovery means. We've used it for fat in the stir sequence. But in this case, we want to suppress the CSF in mostly brain and spine imaging, and mostly CSF. So fluid is really the free fluid, and the free fluid is mostly CSF. The free fluid has the longest T1 of all. So also the inversion time that you use to suppress the fluid is very long. You see at 1.5 Tesla is 2500 milliseconds, so it's more than 2 seconds. The good news is that we don't have the problem that we had with stir, because by this time, all the other tissues that we care about will have relaxed. So the contrast between the signal from the tissue will be fully recovered when we actually suppress the CSF. Normally, this is well, always I would say it's a T2 weighted turbo spin echo image, and it looks like this. So you see that the ventricles here are black, and inside you have T2 contrast with a white matter that is darker than the gray matter. In another district of the body, reducing a little bit the inversion time, we suppress another fluid, which is the blood. The blood is contains cells and contains solutes much more than the CSF. So its relaxation times are much shorter than the CSF, but they're still significantly longer than normal tissue. So in this case, at 1.5 Tesla, to suppress blood, you would have an 830 milliseconds of inversion time. In this case, this is an example of dark blood imaging. Usually we use a trick to avoid losing signal from the tissue, which is we actually do 2 inversions. We don't just do an inversion and then acquire, but we do a global inversion pulse that inverts the signal everywhere. And then we do a localized inversion pulse that only inverts one single slice that we want to image. So this inverted signal in this single slice will have all the spins inverted in the slice, so the tissue will go back to its original magnetization. And by the time we actually acquire the signal, the blood that was re-inverted will have moved out, and so you will have a dark signal from the blood and a nice signal to noise in the tissue. So it's still another inversion recovery sequence, in this case used for cardiovascular imaging. but they're all kind of the same. And then still in cardiovascular imaging, you can also want to suppress the tissue. So we suppress the CSF, we suppress the blood, we suppress the fat. The only thing that is left to suppress is the tissue. And one could say, okay, why would you suppress the tissue? What's the point? But in this technique, the late gadolinium enhancement is a very, very much used technique in the heart. We actually want to suppress the normal myocardial tissue because we want to highlight the tissue that retains gadolinium. So we inject gadolinium in a person, and this gadolinium will accumulate in the tissue where there is a lesion that can be a scar or it can be some active pathology. And then we do this inversion recovery pulse with this inversion recovery sequence where the healthy myocardium is targeted and nulled. And here you obtain this very nice depiction. The myocardium is dark except for the lesion here, which is bright because it has a shorter T1 due to the gadolinium. And finally, there is another inversion recovery sequence. In this case, we don't actually want to suppress anything. We want to use it to enhance the contrast. And this is the case of the MP-RAGE sequence. MP-RAGE stands for magnetization prepared rapid gradient echo. And the magnetization prepared is, again, an inversion recovery preparation pulse. This is the additional bit that is almost ubiquitous. So a lot of sequences that you've seen have this inversion recovery pulse. So the goal here is to have a T1 weighted image of the brain. And this is the goal that we want to obtain. And we are mostly interested in this very, very nice contrast between the white matter and the gray matter. This is a T1 weighted contrast. So the white matter is bright and the gray matter is dark. If we do this with a normal saturation recovery sequence, so the very basic sequence that I briefly showed in the beginning, we see that when we reach the steady state, so after we have a reasonable inversion, with the normal acquisition parameters, we have the white matter and the gray matter that do have different signals. This is the signal level. And the gray matter is a little bit darker, as we expect, and the white matter is a little bit brighter, but the contrast is very bad. And you see the signal level to obtain this contrast is quite low. So we have a relative signal of less than 0.1. So what we can do instead of just doing a saturation recovery pulse, we do a inversion recovery pulse. And then we let the gray matter and white matter evolve. After around 1000 milliseconds, so after around 1 second, we see that the difference between the signal from the white matter, which is the blue one, and the gray matter, which is the orange one, is the highest. So we can exploit, if we rescale these to the same scale as this plot in the left, we see that the white matter has a very high relative signal, and the gray matter has a much lower relative signal. So we have this very nice contrast, and this is exemplified here. You see the white matter and gray matter. There is a little bit of contrast, as you can see, but once you do this inversion recovery, you have this very nice delineation of the structures. This is very used. I mean, it's the most used clinical structural sequence in brain imaging, and it's also used, for example, a lot in fMRI studies because it's the anatomical reference for all the fMRI studies. Okay, so based on what we have said, what is the sequence that has the longest inversion time? The flare sequence, the dark blood sequence, or the late gadolinium enhancement sequence? Right in the chat. Yes. Very good. So the consensus seems to be 1. And it is indeed the flare sequence, because the flare sequence wants to suppress the CSF, and the CSF has the longest T1 of all the tissues in the body. Okay, so yes, the SMRMB office. Oh, yeah, sorry, I was distracted by the chat, but it's not for me. So just to recap, brief recap, there is a flare sequence. We want to suppress the CSF, mostly using neuroimaging. Then we have the dark blood sequence, which is used in cardiac imaging, and the late gadolinium enhancement, which is used again in cardiac imaging, and we want to suppress the healthy tissue. And these are in order of decreasing inversion time. And then the MP-RAGE, which is used in neuroimaging, is a little bit different. Here we don't want to suppress anything, but we want to enhance the contrast to have a better delineation of white and gray matter. Does anybody have any question? Now I will not steal Francesco's job, and I will let him read the questions.
Okay, nobody has a question. I do have a question real quick.
Ah, fantastic. You're very interactive always.
I think you showed, when you showed a flare image, I think it was also a fat suppressed one. So my question would be, maybe I'm wrong, maybe I didn't see it correctly, but I think we usually, sometimes at least, use the fat suppressed flare images in the clinic. So my question is how you pull off suppressing both fluids and fat with the same sequence. Can you still use a T1 method? No, I don't think so, because fat is at the beginning and fluid is at the end.
Yeah, exactly. No, usually you put a fat saturation pulse right before you do the acquisition. So there are some sequences that use 2 inversions, but of course then the 2 inversions kind of interact with each other. So you have to time them correctly. It's not trivial, but I think they're not really used for CSF and fat. They're more used to suppress like fat and blood, which are closer. But one very famous sequence that I think now Siemens has as a product is the MP2-RAGE sequence, which is a variant of the MP-RAGE sequence that actually uses 2 inversions. 2 inversion times, and it can also estimate T1 map and other good things. But I'm not a neuro person, so I'm not really looking too much into it. But there are these class of sequences as well.
Okay, thank you. That makes sense, because I think also in fat suppressed flare images, we often see busier inhomogeneities, right? So it makes sense with the fat sat strategy. Thank you.
Yeah, you're welcome.
I don't see any questions, so I think we can proceed.
It's okay, we can move on. We still have some ground to cover. I promised you that we would also look into unexpected places. So it's not just the normal image that we see, but I want to attract your attention to something that is often neglected, which is the phase component of the signal. So already with the Dixon method, we have seen that the complex signal can be useful, because the fact that the fat and the water go in and out of phase already gives some useful information. But maybe there is more information there. So what you actually have, when you have a double echo experiment, to say, usually what you see is the T2 decay or T2 star decay, depending if it's a spin echo or gradient echo. Let's say if it's gradient echo, you have your T2 star decay, T echo 1 and echo 2. But what you don't see is also this phase component of the signal, which measures how much the spins have traveled since the excitation. And of course, if you have a signal in homogeneity, if you have a Bézier inhomogeneity, this phase, the spins will travel faster, because they will have a higher Larmor frequency because of the inhomogeneity, and so they will accumulate some phase. And so the longer you wait, the more phase you accumulate, and you have something like this. This is a echo 1, and this is echo 2. And you clearly see that there are these phase drops, because the phase, after you acquire 2 pi phase, a 360-degree phase, then you start again from 0. So here, when it gets white, it's close to plus 180, and then it abruptly goes back to minus 180. That's why you have these phase drops here. So the phase accumulation can be due to B0, can be due to tissue characteristics, or it can also be due to gradients, because when we apply a gradient, we induce a B0 inhomogeneity that is spatially dependent. So the first application, or the most logical application of this, is to have a susceptibility weighted imaging, which helps seeing, for example, the iron deposits in the brain. And this will be actually the topic of a future module, so I will not go into detail about it. What I will talk a little bit more about is the flow imaging, because this is an example of what we do when we use the gradients to manipulate the phase. Let's imagine that we have a spin in a tissue, and then we apply one gradient like this. So this gradient will modify our Larmor frequency at this point by a positive value that is corresponding to this intensity that we have here. So while this gradient is on, this spin will rotate due to this gradient intensity and this Larmor frequency. After a while, we turn the gradient off, and then we invert it. So we apply the same gradient, but with opposite polarity. In this case, we keep this gradient on for the same time as before, and the spin will go to the same position. So no phase acquired. Very boring. But what happens now if we have a spin in blood? So this will not stay still. So while the gradient is active, this will increase its phase, but it will have travel. So it will not always experience the same phase as we had when it was here, because the gradient gets weaker in this direction. Then when we invert the gradient will be low enough that it cannot obtain, that it cannot go back to its initial phase value. So it will have acquired a non-zero phase in the end. And this phase is directly proportional to the velocity that this spin was having, the average velocity that the spin was having from the beginning of this gradient to the end of this gradient. This is called a bipolar gradient waveform, and this is the basics of phase contrast flow imaging, which is, well, actually it requires 2 scans because we have to compensate for the other phase effects. But we can see that with this method, we can measure the velocity at each point in our image. In this case, we applied one gradient in the through plane direction, and this is the aorta, ascending aorta and descending aorta. And if we go and measure this gray level value here, this is the phase image, they are directly proportional to the velocity of the blood. So through plane is the common acquisition, but we can also do more complex acquisitions than through plane. For example, we can acquire in-plane flow, and we can even acquire 3-dimensional flow. So we can acquire flow in all 3 spatial dimensions. And then we obtain images like this, where we can reconstruct the flow in 3 dimensions. For example, here it's in the aorta. And here, instead, we have the flow inside a brain aneurysm. And we see that we can highlight these very complex flow patterns because we can really capture the velocity in all dimensions. So this is something a little bit that I didn't say explicitly, but maybe you know. What do we need to obtain the phase image? If I want to look at the phase image, what do I need to do? Is it a separate acquisition? So I acquire first the magnitude of the signal, and then I do another acquisition where I acquire the phase, or I already obtain the phase and the magnitude, and I just have to tell the system to visualize the phase to see it. What do you think? Okay, we have one volunteer for separate acquisition. Others are for enabling it in the reconstruction. And in fact, yes, you don't have to do a separate acquisition. Every time you acquire an MR signal, you also have the phase signal. You just have to enable it. Not all the sequences allow you to visualize the phase image, but in principle, you always have it because it's a component of the signal, and so you just have to visualize it. Usually, in the scanner, it says reconstruction mode, magnitude, or magnitude at phase. Okay, so the phase contains very important information. On the one hand, we can enhance the contrast of local inhomogeneities. You will see this in a separate module. Or you can see or we can use to visualize velocity-dependent phase differences, which is already a quantitative method, which is called phase contrast. So we can directly measure, not just know that there is something moving, but we can also know exactly the velocity at which it's moving. Do we have some questions before we move to the last part? This was short part.
Yeah, I think we can proceed.
Yeah,
and
let's
then we
proceed.
take questions after.
Okay, in this last part, I would like to go a little bit beyond the contrast. So we've already seen that with the phase contrast imaging, we already obtain some quantitative data that are beyond the contrast. Also, the Dixon method can give you some information. But let's take a step back and reflect a little bit on our imaging experience. So what is this? This is clearly, what kind of sequence is this? Well, it's not really a question. This is not an MR image. This is a CT image. Could be similar to some UT image, but it's not. This is a CT image. And next to a CT image, I have a color bar, a gray level bar. And can I put some units here? We all know that this bar corresponds to Hounsfield units. When we have CT, we know that a certain level of gray corresponds to a certain amount of Hounsfield units. So we know that if I go and measure here 40, then this is 40 Hounsfield units. And it's a property of this specific tissue. If I have an MR image and I go and measure here value of 71, it's 71 watt. Can we put a unit here? No. Because if I take another image for a different coil, for example, this is the same acquisition, but a different coil, I have 37, it's a different value. So this 37 or 71, it's not an intrinsic value of the tissue. This is depending on a lot of factors that are not just the physical property of the tissue. So the MR signal depends on the coil sensitivity, depends on the proton density, depends on the T1, T2, T2 star, diffusion, whatever. And usually all these effects are mixed together. And actually the coil sensitivity and the proton density, you cannot decouple one from the other. So what is quantitative imaging? In quantitative imaging, we want to measure and probe the physical characteristics of the tissue without all the other confounding factors. So we want to have an image that only whose intensity is only proportional to T1 or to T2 or T2 star or to fat water. Or in the case of phase contrast, for example, of velocity. We have an image that whose gray level was directly proportional to velocity. So we basically only have one way of doing it. Since every image always depends on a number of factors, we can only extract quantitative values from multiple images. We have to acquire multiple images with different contrasts, and we vary one single parameter and see how the contrast changes. And then from these, we can extract the quantitative value that we want. I will make an example now, which is hopefully much clearer. So we have the inversion recovery preparation. Let's acquire multiple images at different TIs, so inversion times. We already know how this works. So one image has this inversion time, it's very short, and you see there is very little contrast between the various compartments. Then we acquire another image at a different inversion time, and we see that it has a different contrast. Then another image, it has another different contrast. Then another image, and the contrast changes again. So each one of these images kind of T1 weighted. But if we go and measure every voxel in this image, we see that the intensity of this voxel, we don't know exactly what intensity it has, but all the intensities together go and form some sort of curve. And we actually know what curve this is, because we know the characteristics of the signal. When we do an inversion recovery, we know that the signal starts from -1 and goes back to its original state by following an exponential recovery curve. So we can draw this line that corresponds to our signal model that we already know. So we already know that the signal recovers with T1 and with Ti in this case. In this factor here, S0 will be everything else, will be the proton density, will be the coil sensitivity, will be the T2 weighting that each one of these images has. But by acquiring multiple images where we only vary T1, Ti, we can go and fit our T1 map by using, well, basically it's just simple nonlinear fitting algorithms. And then we obtain this map. And then when we go and measure the value of each point in this map, this will correspond to the T1 value of this tissue. You can do the same with T2. You know that different echoes in a spin echo sequence have a different value of have a different contrast depending on T2. So we acquire one image with some echo time, and we obtain this kind of image. We get an image that after a longer echo time, and we have an image that's more T2 weighted, and then again. And again, we know that this decay, depending on TE, will depend on a very clear signal model that is, in this case, not an exponential recovery, but an exponential decay. Again, like before, we fit this model through these points, and we obtain a map. And if we go and measure the values in this map, we will obtain the T2 values of each tissue. In this case, you see the myocardium is much lower than the blood because the blood has a much higher T2 than the myocardium. So these are the basic methods to measure T1 and T2. There are more faster methods that use different signal descriptions. For example, you can use the variable flip angle method. And in this case, the variable flip angle, you acquire two different images with different flip angles. And you see that, again, the signal depends on this E1. It's more complex, but it still depends on T1 and partially on T2 star. So if you change the flip angle, you will change the dependencies on T1, and then you can acquire an image. Again, a T1 map. This is very much used because this is a 3D method. It's used in the brain. Or you can use different acquisitions. For example, this is a continuous SSFP acquisition, and we know that it depends in a complicated way on T1 and T2. So if we fit this kind of signal, then we can obtain T1 and T2 at the same time. So as long as we can describe the signal in terms of the parameters that we vary, so we describe the signal in terms of T1 and the flip angle, then we know the flip angle, and we obtain T1. Then we can use one of these methods. Quantitative imaging is used as shown in cardio because I worked a lot in cardio, but it's used also liver, musculoskeletal, neuro. And if you want, you have I have this Jupyter notebook that you can try, and there's very simple T1 and T2 mapping. Remember, bit.ly/try-QMRI. I'll just write it here, bit.ly/try-QMRI. It might not work right now because the Jupyter changed something, and the interactivity might not work. But you can try it, and I will try to fix it in the next few days if it doesn't work. This is what you can see. Usually you see this image with an example data set. You click here, you see the curve across the TIs, and then you can you can do the fitting and see how it works. In the last few minutes that we have, I would like to talk about QMRI that you can do when you don't actually know the signal model. So all the previous examples were relying on the fact that you could analytically describe the signal. But sometimes this is not possible because the signal is very complicated. It has many imperfections, so you don't have a formula that describes the signal. So what you do is you can put all the parameters that you know of your sequence. So you know that it's, for example, a spin echo sequence with multiple echo times, and this echo spacing and this slice profile and so on. And you can simulate all the possible signals that this sequence can produce based on a combination of unknown parameters. This is an example of musculoskeletal MRI, of muscle MRI, where we can measure the T2 of the water component without the fat, and also at the same time extract the fat fraction, and also acquire the B1 inhomogeneity map. This is relying on signal simulation, and then you do, once you simulate the signal based on many combinations of these three free parameters, you just compare each signal that you acquire with every signal that you have simulated. This is called the dictionary matching, and then you can obtain the triplet that generated the signal that is most similar to the one that you have acquired. This concept has been brought kind of to the extreme consequence in MR fingerprinting. This is the very last topic that I will talk to you about. In MR fingerprinting, you remember in quantitative imaging, you were acquiring images by varying one single parameter. You were varying the TI, or you were varying the T or the flip angle. Now you vary everything, more or less at random. So you make a sequence that is completely crazy. And then you vary all these parameters. You vary the TR, you vary the flip angle, you vary the T, you put inversion pulses, so that the signal is as crazy as possible. But still, by doing this, you sensitize the signal to a number of parameters. So you put sensitivity to T1, to B0, to B1, to T2, to diffusion, to perfusion, to whatever you want. And then you simulate all the possible signals. So you put all the parameters that you know your system is sensitive to, and you simulate the signals that are produced by this sequence. And finally, you do a dictionary matching. And if you acquire enough images, so in this case, for every slice, you acquire very badly and low resolution undersampled images. But inside each voxel of this image, if you follow the image intensity of this of each voxel of this image, you will see that there is this signal with a lot of noise superimposed, but which follows the shape of one of the simulated signals that you have. And then by choosing the optimal signal that best explains your crazy signal that you have acquired, you can obtain them quantitative maps, just like we did before, that can have T1, T2, in this case, the proton density map and the B0 map. This is from a paper, and this is an example in the brain. So in principle, you can sensitize your sequence to everything. You just have to then take care of that in your dictionary. In practice, it's often very much used for T1 and T2 imaging. This is an example in the heart, where in as low as 4 heartbeats, you can get a T1 and T2 map with this strange sequence where flip angle varies in this crazy way, TR varies in this crazy way, then you have T1 and T2 preparations. This is an example in the breast. Again, you get a T1 weighted T1 map and a T2 map. Here is an example in the prostate. So this concept you can basically apply it to every district of the body. Again, here it's a T1 map, T2 map, and they're compared with diffusion weighted maps. And this is, in this case, it's interesting because here it's extracting also the fat fraction. Here is meant for the liver, so you can measure the fat in the liver and you measure the B0 map, also with a MR fingerprinting approach. So, final question for you. We're almost finished. After what I've seen, what do you need for quantitative MRI? Do you need a special MRI system that is calibrated and then you can extract the values? Or any MR system can do quantitative MRI, but you need multiple acquisitions to extract one single parameters? Very good. I am very proud of you. You are all replying. And indeed, this is the result. And so what is important is that you acquire multiple acquisition with one or more varying parameters. If you have an analytical expression, use that. Otherwise, you can use simulations. And however, remember that the map that you obtain is only as good as your model. So if your model contains all the possible parameters that can influence your result, then you will get an accurate map. But the models often cannot take everything into account. You have a diffusion, you have perfusion, you have magnetization transfer, you have B1 and B0 in homogeneity. So you can never have a model that really takes everything into account. So you will always have imperfections in your quantitative maps, and your quantitative maps will always be dependent on the method that you actually use and on the model that you actually use. Okay, thank you very much for your attention, and last round of questions if you have them. I killed you all. Now you're all
I ran out of questions too.
very good.
I mean, because you were being very thorough in explaining everything, so.
Okay, thank you. It's not because you just phased out and
not at all.
Playing Wordle and the other. Very good.
Yeah, I would just ask you curiosity. Like, I don't know if that's been done or something. MR fingerprinting. So right now, you would get the signal by modifying the parameters and then try to match the dictionary, right?
Mm-hmm. Yeah.
I was wondering if somebody tried to do that with deep learning instead.
Yes.
I don't know if you know that. Yeah, of course they did.
Yeah, I mean, as a general rule, if something has been done, it has also been done with deep learning. So okay. By now.
Do you think it has advantages at all, or not really?
So people report that for very large dictionaries, deep learning can be much faster and much less memory consuming.
Mm-hmm.
But it depends. I've also heard of people that were telling me that they tried and didn't really work well. But yeah, maybe it's just a matter of finding the right architecture, finding the right training set, and so on. But yeah, I mean, it can help instead of doing like brute force. dictionary optimization, you can try deep learning.
Gotcha. Thank you. We'll just give probably like 10 seconds more if somebody comes up with a question. Otherwise, we can wrap up probably.
Stop sharing.
Okay, I think everybody's very happy with everything that you explained, and we don't have any questions anymore.
Very good. You're all exhausted. Okay, then thank you very much for joining. And yeah, my job is done for this year. Hopefully see you next year.
All right. Thank you very much for your classes. Keep in touch.
Thank you. Bye.
Bye, everybody. Have a good night.